Hello everyone, welcome to this lecture of hyperbolic geometry. In this lecture, we will learn about some basics of hyperbolic geometry. Hyperbolic geometry, it is a part of non-Euclidean geometry. So here, the fifth axiom of the Euclidean geometry is violated. So in this lecture, we will learn about hyperbolic plane. So we'll be providing here the upper half plane model of the hyperbolic geometry. So there are other various models, so which we'll discuss later. So we'll be describing hyperbolic plane. So we'll be describing a plane geometry where the fifth axiom of Euclidean geometry is valid. So first we'll be describing the upper half plane model of this hyperbolic plane. So what is this? So let us begin with this upper half plane. So what is this upper half plane? So this is the ordered pair x comma y belonging to R2. So that is both x and y are real numbers and this y is positive. So this is my upper half plane and we put topology on this upper half plane to be the subspace topology induced from R2. And this upper half plane will denote it by H2. So the topology on H2 is induced from R2. So where this R2 is endowed with usual topology. So this H2 with the subspace topology coming from R2, it is a subspace of this R2. So now we are going to give a metric on this upper half plane. So that metric, I'll call it to be hyperbolic metric or Poincare metric. So to understand that metric, first let us go through this formula. So first we'll give this formula dA squared equals to dx squared plus dy squared by y squared on this upper half plane. So this formula will give you a metric on this upper half plane. I'll come into this thing. So, but before that, so let me explain what do you mean by paths and differentiable, piecewise differentiable paths on this upper half plane. So what do you mean by path? So a path is just simply a continuous map alpha from this closed interval AB to H2. Okay, so that is, so if I take this upper half plane and so these are my 2 points alpha A and alpha B in H2 and this image of alpha, so this is this path joining this alpha A and alpha B. So this is the image of alpha. And what is the meaning of piecewise differentiable path? So a path alpha is said to be piecewise differentiable if there existed a partition of this closed interval AB such that so alpha restricted to each of this subinterval is differentiable for all I equals to 0 to I equals to 1 to n. Okay, so that is, so what is the meaning of alpha restricted to this interval ti minus 1 ti is differentiable? So that is, so this limit h tends to 0, alpha t plus h minus alpha t divided by h exists for all t belonging to this interval and for all I equals to 1 to n. So this is the meaning of a path alpha to be piecewise differential. So now given a path alpha and given this formula d square equals to dx square plus dy square by y square, so we can compute the length of this path. Okay, so let us see that thing. So let me again write down this formula. So we are given this upper half plane and we are given this formula d square is equal to dx square plus dy square by y square. So this ds, it is called the line element. So now suppose a path is given in H2 which is piecewise differentiable. So then, so this alpha of t, so this will be equal to your xt yt, and this belongs to your H2 subset of this R2. So because H2 it is a subset of R2, so image of alpha, so it will be this ordered pair xt and yt. So image of alpha t will be this ordered pair xt yt. And we are given this alpha to be piecewise differentiable. So this means that so this this components xt yt are both piecewise differentiable. So now, so given this path, we can compute the length of this path alpha. So length of alpha, so length of alpha, so this is denoted by L alpha. So this is defined to be integration a to b root over dx dt square plus dy dt square divided by yt. dt. So this integration will give you the length of this alpha. So because this xt and yt, so these are piecewise differentiable, so therefore this thing, it makes sense. So dx dt dy dt, whenever it exists, it makes sense. And again, because it is piecewise differentiable, so this integral also, it makes sense. So this is the definition of length of this alpha. For instance, if I take this map, so alpha t, it is your 0 comma t. So t is varying from this closed interval a to b. So then, so what will be my length of alpha? So this will be integration a to b. Now xt is your 0. So you have root over. So xt is 0. So dx dt automatically it will be 0. And dy dt, it will be what? So xt is 0. Yt is your t. So dy dt, so it will be your 1 divided by t dt. So this is basically integration a to b dt by t is equal to log b by a. So here this length of this path, so if I take this upper half plane, so length of this path from this 0a to 0b, so length of this path is nothing but log b by a. So this length, so this will be called to be the, in fact, the hyperbolic length. Hyperbolic length of this alpha. So instead of this y square here in this formula, if I take ds square equals to dx square plus dy square, and in the denominator this y square is not there, so we'll get the Euclidean length of this alpha. Yeah, so this length is differing from the Euclidean length. So that's why I have written it is hyperbolic length. So next is, so this upper half plane, so this can be written in terms of complex number also. So in terms of complex number, so this is set of all complex number z belongs to your C, where this imaginary part of z is greater than 0. And the square of the line element also it can be written in this way. So d square is this mod of dz square divided by the square of imaginary part of z. Okay, so again, so what is my dz? So dz, it is dx plus I dy, and z is equal to your x plus iy. So in terms of complex number notation, so d square is equal to this. So this square of this line element written like this, or in terms of complex number, will be called hyperbolic metric or Poincare metric. So now, so given 2 points in this upper half plane, so what will be the distance between those 2 points with respect to this hyperbolic metric. Okay. So let us take 2 points. ZW belongs to your upper half plane. So the hyperbolic distance, so this I will denote it by dh2. So the hyperbolic distance between z and w, so this by definition, it is the length of, it is the infimum of length of gamma, where this infimum is taken over all piecewise differentiable paths gamma from z to w. So this is the definition of the distance between 2 points. So one can check that. So this dh2, it is indeed a metric. So h2 with this dh2, so it will be a metric space. Yeah, so this is the exercise. So this dh2, so this is in fact it is a function from this upper half plane cross upper half plane to set up all non-negative numbers, real numbers. So the first one is, so dh2zw is equal to 0 if and only if z is equal to w. Second one is the symmetric thing, the symmetric property. So dh2zw is equal to your dh2wz. So the distance between zw is same as the distance between wz. So this is the symmetric property. And the third is this triangle inequality. So distance between zw is less than equals to distance between zu plus distance between u and w. So for all z, w, u belonging to this h2. Yeah, one can prove that. So this distance function, so it is indeed a metric in some lecture. So what I'll prove is the following. So this will violate the fifth axiom of this equality in geometry. So if I take this upper half plane, so this is my upper half plane. Now if I take any 2 points and suppose they lie on a vertical line. So then suppose this z and w are these 2 points, it lie in a vertical line. So what I'll prove is the following in some lecture. So if I join this zw by this vertical line segment, and if I take any other path gamma, and we assume also this gamma to be also piecewise differentiable, and let us assume this alpha to be this vertical line segment. So we'll prove that, so this length of alpha, so this will be less than equals to length of gamma. So this means that, so alpha is the shortest length path joining this ZW. And now if I take any 2 points, which does not lie in the vertical line. So then so let us join this ZW by an Euclidean line segment, and let us take the perpendicular bisector of this line segment. So this will meet the x-axis at some point. Let us take it to be P. So therefore, this distance between PW and PZ, so this will be this Euclidean length, it will be equal. So then I can draw a semicircle with center at P and radius distance between P and Z. So that distance, I'll take it to be the Euclidean distance. So what I proved that I can draw a semicircle passing through ZW with center at P, and the P lies on the x-axis. Yeah, so given any 2 points ZW, if ZW does not lie in the vertical line, so there exists a semicircle with center at P and it passes through Z and W. And this P, it lies on the this x-axis. Okay. Now, if I take this portion of the semicircle joining this ZW, so this path, again, it will be of shortest, meaning if I take any other path, gamma, and the earlier semicircle circular segment, if I call it to be alpha, so the length of alpha, it will be less than equals to length of gamma. So what I'll prove that paths of shortest length are vertical lines, part of the vertical lines, or part of semicircles whose centers lie in x-axis. So now in this, suppose we have this thing. So in Euclidean geometry, so lines also are the shortest length path joining any 2 points. So the shortest length paths will be called to be geodesics. So now if I take this upper half plane, so this is my upper half plane, and we put this hyperbolic metric here. Now you take any point Z and take any geodesic. So take any geodesic which does not intersect Z. So there exist infinitely many geodesics passing through Z and not intersecting the given geodesic. Let us take that given geodesic to be L. So Z is not lying on this L. So there exist infinitely many geodesic passing through this Z and not intersecting this L. So that is very easy to see. So first of all, if I have this diagram here, so this vertical line, so this will not intersect this L, and you can have infinite semicircles whose center lie in real axis and it does not intersect this L. So you can draw many semicircles like this. Okay. So there exist infinitely many geodesics passing through Z and not intersecting L. So this violates the fifth axiom of Euclidean geometry. So I'll stop here. In the next lecture, we'll learn about isometries of this upper half plane, and then we'll be proving uh, the geodesics of the upper half plane are vertical lines and semicircular arcs.